Data types matter. Here's some examples of why. June 4, 1996, we had an unmanned Ariane 5 rocket launched by the European Space Agency. Exploded 47 seconds after liftoff. It was on its first voyage after a decade of development costing $7 billion. A destroyed rocket and its cargo were valued at $500,000,000. On February 25, 1991, during the Gulf War, an American Patriot missile battery in Dhahran, Arabia, failed to intercept an incoming Iraqi Scud missile. The Scud struck an American Army barracks and killed 28 soldiers. And it was a data type problem. On July 23, 1983, at 41,000 feet somewhere over the Canadian countryside, Air Canada 143 suddenly was without fuel, despite its computers indicating there was plenty of fuel remaining in multiple tanks. With its fuel gone, so was its electrical and hydraulic systems. And the 767 had become really a flying brick. It's amazing that they actually were able to land the thing. Fuel loading was miscalculated due to a misunderstanding of the recently adopted metric system. Okay, so what we like to do next is look at signed integers. This is a little more complicated than unsigned integers, as you'll soon find out. Integers of n bits have 2 to the n distinct values, so we can cover 2 to the n numbers with n bits. Signed integer assigns about half the positive integers to the positive integers and about half to the negative integers. There's several ways of doing this. Some are better than others, as we'll soon find out. That leaves, if you do signed integers, and the first bit is the sign, we have 2 values for 0, or one for 0 and an extra. So the most significant bit indicates the sign. It's 0 if it's positive and 1 if it's a negative, and that works on all systems. Examples are sign magnitude. Okay, so sign magnitude is what I was just talking about. If you have an unsigned number, we just add 1 bit to the left of that unsigned number, and that bit would tell what the sign is. The problem is when you do that, well, we'll look at that. There are problems. Then there's also 1's complement. 1's complement means you just change all the signs of the bits. And that will also give you a negative number. So if you want to change the sign on something, just change all the 1's to 0's and all the 0's to 1's. And 2's complement, we'll look at that. That's a little more complicated. So positive signed integers are treated just like unsigned integers in the most significant bit. So if you have, say, 5, you could add 5 to it, and you'd end up with 10. Negative signed integers have a 1 in the most significant bit. So signed magnitude would be 1, and then 1 or 0, 1, 0, 1, and that would be a -5 for signed magnitude. 1's complement, you just change all the bits of the 0, 0, 1, 0, 1 and make it 1, 1, 0, 1, 0, and that would be -5. 2's complement, well, -5 would be 1, 1, 0, 1, 1, and to get there is a little tricky. We'll talk about that in a minute. So signed magnitude integers, let's look at that first, because that looks like maybe the most logical thing to do, so let's check it out. So we got 15 would be 0 with 4 1's. -15 would be 1 with 4 1's. 0 would be 0, and -0 would be 1 with 4 zeros after it. So there's actually two values for 0. The range would be minus, and then quantity 2 to the n minus 1 minus 1, to 2 to the n minus 1 minus 1. And the problems? Well, 2 represents representations of 0. That's not good. And it turns out arithmetic circuits are complex and cumbersome. Very difficult to add these things. Negation and absolute value operations are very easy, but addition and subtraction operations are difficult. So to negate a number, you just toggle the first bit. 1's complement. Okay, well, that had some problems, so let's look at 1's complement. Maybe this would work better. So representations, there's a 6, a 1, 1, 0. And a negative 6 would be 1, 1, 0, 0, 1. You would have 0 being a 0, and also all 1's is a negative 0, which is the same thing as a 0. The range is the same as last time. The problems are, well, so far the same as last time. 2 representations of 0. Arithmetic circuits use binary addition with end-around carry. The resulting carry out of the most significant bit of the sum is added to the least significant bit of the sum. That's a little bit trickier, but not quite as bad as sign magnitude. And to negate a number, you just invert the number bit by bit. So that's easy. So 2's complement. How do we do 2's complement? Well, the representation for positive is still the same as it always was. Negative 6 looks a little different, though. It's 1, 1, 0, 1, 0. And 0 is 0, and 1, 1, 1, 1 is negative 1, so there aren't really 2 representations of 0. You've got an extra, you're using one more, you have one more negative number than you do positive number. And actually the logic for the logic that's needed for addition and subtraction is just much, much simpler. So the bottom line is it's simple and faster hardware units. To negate a number, you take the 1's complement and add 1. So the left bit still encodes the sign. If you see a 1 there, it's negative. So how do we do a 2's complement integer? If a number is positive or 0, just the normal binary representation. If the number is negative, start with a positive number, flip every bit, that's taking the 1's complement, then add 1. So here we go. Let's try negating 5, finding negative 5. So we start out with 5, 0, 0, 1, 0, 1. Do 1's complement, which is 1, 1, 0, 1, 0. We add 1, which gives us 1, 1, 0, 1, 1, and that's negative 5. Here's an example with 9, and you can fill in the blank there. What goes in that blank? There it is. And then you add 1, and that's what goes in the blank. So that's how you do multiplying by minus 1. So positional number representation with a twist. That's what 2's complement is. You know, and normally you'd have 2 to the 0, 2 to the 1, 2 to the 2 to the 2, or so on. You know, but the highest 2 you have, you just need to put a negative in front of it. So one way of doing that is if you wanted to get negative 6, you add minus 2 to the third plus 2 to the 2 plus 2 to the 1, and you get, I guess trying to get minus 2. So that would be minus 2 to the third plus 2 to the 2 plus 2 to the 1 gives you minus 2. Okay, so n bits represent numbers in the range from minus 2 to the n minus 1 up to 2 to the n minus 1, and then subtract 1 from that. So what are these 2's complement numbers? I'll let you look at this right here. Start out, the first one's easy, it's 0. The second one should be pretty easy, see if you can figure it out. Alright, it's 6. The next one, what is that? Well, that's actually not too bad either. It's the highest negative number, -1. And the next one, well, you can use this thing here. It would be -2 to the 3 plus 2 to the 1. So that must be 8. Must be -6. Yeah, there it is. And that one's 1. And this one is, I think it's going to be -8. And I'll let you think about these for a minute. Another minute on this one, probably a little harder. And another minute on this one. And one more. Yeah. So, here's a quiz for you. We'll let you complete this quiz, and then you can go on to the next lecture.